Whenever you store energy, there is a chance for that energy to be released in ways you're not intended to use it. That could become a hazard. What has been happening with, in particular, lithium-ion batteries, that they have becoming more powerful. With more energy stored, there are more ways in which things could go wrong. It is important to be able to predict and study the ways in which the energy could be released in an uncontrolled fashion, and the potential consequences that can come up with. That might be a fire or simply malfunction of the battery. That will be a more benign. But among the realm of things that could come to happen is the release of a flammable off-gassing that could then ignite and create other hazards. It is important for you, if you are going to have one of these facilities, to know the kind of hazards that you'll bring along with it, and if that challenges in any way the things that you have in place around it. The purpose of this test was to be able to collect data on the strength of the explosion that will come out should an internal cloud develop within a battery energy storage system. We decided to test with the standard shipping containers because some of the battery energy storage systems that you see out there, they look very much like that. This test will demonstrate the kind of consequences that come to happen if you have no way to mitigate an internal deflagration scenario. We basically test two levels of concentration. We tested an enclosure that was filled with a deficient amount of battery gas. So we injected an amount of gas that was not the optimum. More gas could have been burned with the air that was inside, but we decided to run short. We also run a different treatment. I injected the stoichiometric amount of fuel. That is the optimal amount of fuel that will burn completely. We noticed that the loads that come out of those two situations, when you run fuel deficient or you run a concentration that is the optimum, we noticed that the loads were very different. In one case, when we ran the experiment in lean, it was a very mild consequence, but in turn, when there was enough fuel to burn completely with the air in the enclosure, the blast load was significant. We tried three different conditions for vent surface area. We left the container with both doors open. We also tried a container with one door closed and one door open. And for the last grand finale, we tried both doors closed. We measured the pressures that will develop on all of them. We know that the more vent surface area, the milder the pressure that will be developed. If you try to contain hot combustion gases in a closed space, they will pressurize. And the more surface area you give them as an exit, the less of a pressure, the less of a blast that will come out of that enclosure. If you try to contain it and something in that enclosure is weak, that will yield and will open. That's exactly what happened in our test. When we set up the doors closed, those being the weakest element on the envelope, well, they were opened by the explosion, and we got the pressure out of that, and we learned what kind of pressures are developed to open those doors. We did a very simple treatment for congestion. Congestion in this context is anything, any physical object that will be there inside and will have an interaction with the flame front. It is well known that the more congestion, the more objects, physical objects, the flame has to interact with, the faster it will go, the quicker it will convert the fuel from chemical energy into thermal energy, and that helps a lot to generate a strong blast. We decided to test two different levels of congestion. One was empty, devoid of anything other than the instruments themselves, and congested with dummies or just boxes, so that the flame now have something to interact with. Let me now show you one of the actual test specimens that we use in this program. What we have here is a shipping container that has been fitted with wooden boxes. These wooden boxes are here to mimic or mock what a battery rack looks like, and they provide a surface, an object for the flame to interact with and accelerate. When these boxes or bodies interact with the flame, you will get acceleration on that frame front and also a stronger shock coming out of here. What we learned is that it makes a very stark difference. When the flame has something to interact with, the blast that you measure out of that container is much stronger. BakerRisk has helped many kinds of battery users, designers, manufacturers. One in particular example that comes to mind is that of abuse test cell that we executed as a safe enclosure. A safe enclosure is a steel enclosure that was designed to contain a worst case scenario of an internal deflagration. It was implemented with deflagration vents that will redirect the explosion and the hot combustion products to a safe location. At BakerRisk, we're particularly well situated to be able to analyze and assess how a hazard could be and design the mitigation measure that will help us stay safe.